Hello, dear student and viewers. Myself, Professor Ashok Kumar, and I'm working in Department of Mechanical Engineering at Dr. Subhash Technical Campus. Today we are going to discuss one more and very much important chapter as far as concern machine design and machine component design. That is chapter number 4, Torsion. And yes, you know that this chapter comes in subject fundamental of machine design. Specially, GTU has offered in fourth semester degree mechanical engineering. And first topic that we are going to discuss is an introduction. Basically, term torsion is very famous, and every instant of your life you have listened this term frequently. Torsion is basically the terms which is directly related with the twisting moment, or we can say that the torque. So in our mechanical engineering, we require frequently transmit power or torque even from one place to other place, from driver to T1. So at that time, if you are finding any mechanical component, for example, shaft or axle or something other pulley or gear, which rotate continuously, and in that way it transmits the power. So ultimately, the torsion is related with the torque or twisting moment. So the definition of torsion, look at the screen. When a structure or machine member is subjected to a moment about its longitudinal axis, the member twist and shear stress is induced in every cross section of the member. If you are finding such a mode of loading, it will be known as a torsion. So over here, the basic or prime condition to set up a torsion in any machine component or rotating component like shaft is that the torque should be applied over there, and application of torque is always perpendicular to the axis of shaft. That means look at the bottommost diagram. There is a one circular shaft, and this is the geometrical axis. So whatever torque applied at the end of the shaft is always perpendicular to the geometrical axis of shaft. So this is the first condition in order to set up or produce the torsion. Whenever you are applying torque, due to other end of shaft is fixed over here. So what happens? Due to application of torque, each and every section of that particular shaft is getting sheared off. That means we can say that the shear stress induced in each and every section. So this is the what the basic mechanism of torsion to be produced. Condition is very similar, and twisting moment is required to have the torsion of any component. So if we are gradually increasing the magnitude of torque, then it may possible that a fiber, or we can say that the layer of cross section of that particular shaft may get deformed. Let's say it will be deformed by theta. So over here, this is the initial layer and this is the final layer. If you are applying more torque, then it will possible that your fiber will get new position, and this phenomena is generally we term it as a shear stress. So if such thing is happening with any machine component, we can say that torsion is there. In our regular life also, we have experienced a numbers of time that we introduce torsion in many machine component or even simple parts. Look at the top diagram. There is a one screw which is screwed with the help of screwdriver. So over here, screwdriver through which we are applying torque, and each and every section of that screw is subjected with shear stress. So ultimately, we can say that there is a torsion in every section of the screw. Similarly, if we are taking one more example, then we know that there is an electric motor, and power or torque from the electric motor need to transfer in turbine. So for transfer of that torque or power, we have used one shaft, transmission shaft. It is coupled at point A and point B with by using coupling. So whenever there is a power that is transmitted from an electric motor to the turbine, at that time torque will be induced, and it is perpendicular to the geometrical axis of transmission shafts. So there are numbers of cross section like this. which is directly affected under the shearing stress. So we can say that the torsion is there in case of transmission shaft between an electric motor and turbine. If we are talking about some common example where we feel experience of torsion, then opening and closing of our house doors, knobs, screwdriver that we have discussed, of course, drill bit, which drill hole in machine component, it will also experience the kind of torsion. Transmission shaft as well as machine spindle are also some examples, common examples. Generally, up to this, now you are able to the prime condition of the torsion, and that is the twisting moment is required. But twisting moment or torque is definitely possible with the help of single moment or couple. That it clearly means that it never means to have the couple or the single moment which is responsible to produce a torque. Generally, torsion cause angular displacement. That means your cross section get deformed on the order of application of external torque, and it creates the shear stress along the entire section of the transmission members. Now, look at the screen, and that is the topic number 2, theory of pure torsion. It is very much important as far as your examination point of view, because this theory plays vital role for designing a transmission shaft, for designing any members with transmitting power or torque. So kindly be focused upon particular this theory, and this theory is only related with the torsion. So we can say that theory is subjected with only torque application. There will be no any kind of consideration of bending moment. So we can say that theory is only and only based upon pure torsion. And torsion, or we can say that the shear stress is produced due to only application of twisting moment. That is the second subtopic that you have to consider. But uh, in practical position, a real manner, you are not able to find any machine component which is only subjected with twisting moment purely. At some instant, anyhow, bending moment is also acting with little magnitude. Some axial force or the lateral forces are also present there. So, if we are talking about general and actual position or actual condition, it is not possible to have such a condition in which the special transmission element are subjected to only twisting moment. Well, before deriving the relation of torque, few assumption has been taken for the easiness of deriving the relation. And first, the consideration is made on the basis of material. So material, whatever the selected for the shaft design and deriving the equation of torque, is homogeneous and isotropic. And exactly it is very similar assumption as that of what we consider in case of bending stress equation. So homogeneous itself means the material made with uniform content. Every cross section contains the same material. And isotropic, that means elastic property remains same throughout the entire section, throughout the any section. So this is the first consideration. Second is the Hooke's law is obeyed by the material. That means due to that what we have discussed, material is isotropic. So of course, the Hooke's law is valid up to proportional limit in this particular material. So stress is directly proportional to strain in short. Third consideration is that shaft is circular in section. So initially, while deriving the torque equation, what you selected shaft is circular throughout in the section, cross section. Fourth one is the whatever the you have selected cross section will remain its unique cross section throughout the procedure. That means after and before application of torque or twisting moment, your section will not change anyhow. So cross section of shaft remain same. Fifth one is the shaft is subjected to pure torque only. That we have already discussed whenever we have started this theory. Because while deriving pure torsion equation, it is prime consideration that The transmission shaft is subjected with only and only pure force or pure twisting moment. Shaft is not subjected to any initial torque. That means there will be no any kind of initial or we can say that the starting torque is available while designing your transmission shaft. And transfer section that you have selected for the shaft were planned before the application of torque, and the same cross section will remain plain even you have applied the torque. That means before and after application of torque, the cross section of shaft will remain plain. So this is the somewhat basic introduction of pure torsion theory and some assumption that we have taken. Now look at the diagram. There is a one transmission shaft, and it is one end is free and other end is fixed with some bracket or say the wall. Now look at the free end of the shaft. There is the application of twisting moment T in clockwise direction. And first of all, kindly consider the small element this fiber A just you have to focus upon. And first step towards deriving this equation is that you have to calculate the strain that is produced in particular section A dash or particular strain produced on point A due to application of torque T. So over here strain of point A will become is equal to deformation per unit length. So we can say that A dash upon L is equal to 10.5. That means ultimately we require this. This is the deformation or strain. So by geometric relation, we can easily calculate the ratio A dash upon small l, that will be equal to 5. So over here it will be the deformation from this origin, C origin, and theta is the deformation of same fiber A dash from this origin. That means theta is located with fiber O, center O. So over here, first of all, you should to calculate the deformation, and deformation is due to application of external twisting moment T. So deformation is equal to A dash upon L, and that is equal to 10.5, and which is easily calculated from by considering this triangle. Similarly, if you are taking origin O and calculating the deformation of point A, then it very easy. A dash upon the whatever the radius R is given to you. So once again, A dash is equal to R theta. Now both of the deformation is the same, whether you are taking it as a origin C or whether you are taking it from origin O. So both of should be equated, and over here both of the relation are equated. From that it will become 5 is equal to A dash upon L is equal to R theta upon L. Now suppose shear stress tau is produced in outer layer or outermost layer. That means for example uh, any you can take it from anywhere. For example, this is the outer layer you are taking for the consideration, and C is the modulus of rigidity or G is the modulus of rigidity. Then ultimately we know that modulus of rigidity, shear stress, and strain or shear strain stand for the relation like that. 5 is equal to shear stress upon modulus of rigidity, or you may also write modulus of rigidity G is equal to shear stress upon 5. Now, just you have to equate both of the equation. In particular, first our relation we have derived the relation R theta upon L, and it should be equated with the equation of shear stress, strain, and modulus of rigidity. So by equating both of that and simplifying it, you will have tau upon R is equal to G theta upon L. So it gives the relation of shear stress with respect to radius of shaft, modulus of rigidity, angular deformation theta, and length of the shaft. So in general way, we can say that shear stress at any layer which is located at a distance x from the shaft will be given as a tau x upon R is equal to tau upon R is equal to G theta upon L. Once again, tau x, that means the shear stress at the layer which is located at the distance x R stand for the shaft radius, which is the modulus of rigidity. Theta is equal to angular deformation that is set up due to application of external twisting moment, whereas L is equal to length of shaft. So this is what the torque equation that we have discussed. After that, very much important topic that we are going to discuss, that is the strength of a solid shaft. Ultimately, strength itself means the maximum torque that can be transmitted by any shaft. It will be indication of the strength of that particular shaft. Or we can say that the maximum capacity of power transmission of any shaft is known as a strength. So, in order to derive the relation of strength, first of all, kindly consider one circular shaft. Look at the top right hand side diagram having the radius capital R. And out of that cross section, kindly consider a simple fiber or simple layer which is located at a distance x from the center of the shaft. Now, first of all, just you need to calculate the area of that particular small element or small layer that you have selected. So it will become 2 pi x into dx. Once you have calculated the area of that particular small layer, now it's time to calculate the shear stress that is produced on that particular area. So we know from the previous slide relation that tau x, that means the shear stress that is produced at any layer located at a distance x is equal to tau into x upon r. This is very simple and already we have discussed this relation in previous slide. Now, once you have the shear stress, you have the shearing area, then it's very easy to calculate shearing force or shear force simple. So now shear force or turning force in other way is equal to shear stress into shearing area. Over here shear stress is there, shear area is also there. By putting the relevant values of both of the terms over here, you will have this relation. And by simplifying this relation, we can write that the turning force or shearing force is equal to 2 pi tau upon r into x square into dx. And now we have derived the shearing force or turning force, then it's very easy to derive the relation for twisting or torque moment. So twisting moment or torque that is act on that particular small elemental area is equal to turning force into distance of element from the shaft central axis. So this is the turning force 2 pi tau upon r into x naught square into dx, and this is the distance as the small layer that what we have considered is located at a distance x from the centroidal axis. So by simplifying that relation, we can say that the dt is equal to the torque that is acting on small elemental area, and that is equal to 2 pi tau upon r x cube into dx. Dear friend, this is the torque equation, but be sure this is the torque only which is acting on small elemental area we have initially considered. In order to calculate the entire cross section, or in other words, we can say that in order to calculate the torque, total torque that is being transmitted by shaft, just you require to have an integration of above equation. And the limit is 0 to r because lower limit is the center axis of shaft and higher limit is the outermost surface that is located at r. So between 0 to r, you have to just integrate this equation, and by simplifying that relation, you will have the pi by 16 upon tau, pi by 16 into tau into d cube, that is the relation for total torque that is being transmitted by a shaft. Now, similar as what we have discussed in previous case, topic number 4 is also topic of strength of a hollow shaft. Just you have to follow the same procedure, but as compared to previous one, here the shaft is not solid, but hollow shaft is given to you. Once again, kindly consider a small elemental ring, and first of all, calculate area of that ring. Once you have calculated area, kindly calculate the shear stress that is produced at a distance x. So tau x is equal to tau into x upon r. After that, consider or calculate the turning force or shear force. What you may like. Turning force is equal to trace into area. So tau x into dA. By putting the values of tau x and dA over here and make simplification, you will have the 2 pi tau upon r into x no square into dx. So this is the magnitude or equation for the turning force. Once you are deriving turning force equation, from that it is very easy to calculate torque, and torque is equal to turning force into distance from the center of gravity, or we can say that the central axis. So by putting the relevant values of turning force from here to here and distance, that is x, and simplifying it, it will give us a new relation, that is a 2 pi tau upon capital R x cube into dx. So this is the small element which transmits the torque dt, but in order to derive the total torque that is being transmitted by entire shaft, just make an integration to this relation. You will have the torque is equal to R to R 2 pi T upon R x cube dx, and further simplification, it will give us a pi by 16 into tau into d raised to 4 minus d raised to 4 upon capital T Newton into mm. This is the relation in case of hollow shaft, which transmit the torque as well as twisting moment. Now, after discussion on strength of hollow and solid shaft, let's have the discussion on few terminology like torsional stiffness, torsional rigidity, and polar modulus. We have already derived this relation T upon J, that is equal to tau upon R, and that is equal to G theta upon L. We know that T stands for the twisting moment or torque, J stands for the polar moment of inertia, tau is equal to shear stress that is produced in any layer or cross section. R is the radius of shaft. G is modulus of rigidity. Theta is equal to angular deflection due to twisting moment, and L is equal to length of shaft. So this is the torque equation. If you are taking the terms tau upon J, that means the ratio of torque and polar modulus or polar section modulus, it will be known as a torsional stiffness. In short, torque required per unit twist is known as a torsional stiffness. Generally, it indicates the strength or capacity against the deflection of any shaft. That's why it is known as a torsional stiffness. Suppose you are taking other parameter or ratio like TL upon theta, it will be in sentence, it will be known as a torque divided by the angle of twist per unit length. So it will be known as a torsional rigidity. If you are taking ratio of torque and the length with that angular deflection, it will be known as a torsional rigidity. It indicates the capacity or strength of any shaft against the deflection or deformation. So this is the torsional rigidity. Now, one more relation can be derived from the equation of torque, and that is tau is equal to T upon J into R. So in that particular relation, if you are taking ratio of J upon R, that will become a new relation, that is capital Z suffix P. So this capital Z suffix P is known as a polar modulus of shaft section. So ultimately, polar modulus is simply ratio of polar modulus of section is simply ratio of polar moment of inertia upon the distance of a fiber, or we can say that the radius of shaft. So this is what some performance parameter that we have discussed. After that, point number 6 is the power transmitted by a shaft, and this equation is very familiar to every one of you, because it comes in first year degree engineering subject, basic of mechanical engineering, to at the end of your graduation. It is very common, and power transmitted by shaft, if you require to calculate, then it's become simple 2 pi nt divided by 60. Over here, power is P stand for the power, that is watts in unit. Torque is equal to T, and unit of torque is equal to Newton into meter, whereas RPM is equal to N. So this is actually simple equation for the power, and generally in case of IC engine, this same equation is known as a brake power equation. After that, topic number 7, that is the polar moment of inertia, and that we all know that the moment of inertia about an axis, which axis is actually perpendicular to a plane, that means axis x and y is known as a polar moment of inertia. That means suppose you are calculating a moment of inertia about axis z is known as a polar moment of inertia, because we all know that axis z is perpendicular to the plane of paper, and the plane of paper represent basically two axes, horizontal axis x and vertical axis y. So if you are finding a moment of inertia in an axis which is perpendicular to axis x and y, simply it will be known as a moment of inertia or polar moment of inertia about z axis. Now this is the relation that we have already derived, that is tau upon r is equal to g theta upon l. And we also know that the equation for torque is equal to T is equal to pi by 16 into tau into d cube. So from that relation, you can convert this equation in terms of tau, and that is equal to 16 into T upon pi d cube. So now by putting the values of tau over here and make simplify this equation, you will have 16 into T upon pi d cube into R is equal to g theta upon l. Further simplification, it will give us T upon pi by 16 d cube into R into is equal to g theta upon l. So ultimately, over here, just you have to make simplification, and at the end, you will have the equation of T upon J is equal to g theta upon l. Over here, this term specifically, we can say that uh, the polar moment of inertia is generally simply the ratio of we can say that it's simply a summation of the polar moment of inertia about x and y axis. So this is the equation T upon J is equal to g theta upon L, in which particularly this term J, that is equal to polar moment of inertia, and it is easily represented in previous slide that T upon J is equal to g theta upon L. So over here pi by 32 upon d raised to 4, that is equal to J. So this is polar moment of inertia. So after completing few theories based on torsion, let's have a few examples that we required to solve. First example, that you have given a hollow shaft with external diameter is 100 mm and internal diameter is 40 mm, which is transmitting power at 120 rpm. So just you require to calculate the power that can be transmitted by shaft, and allowable shear test you have given, that is 50 megapascal. Dear student, it's very easy to solve this. Just you require to calculate power that can be transmitted from the shaft itself. So first of all, just go through the basic equation of torque. T is equal to pi by 16 into tau uh, bracket d raised to 4 minus d raised to 4 upon d. Uh, by putting that relevant value, you will have the torque at the end, 9.56 kilonewton into meter. And now we know that the equation for the power or brake power is equal to 2 pi nt divided by 60. Put all that value over here, T that you have already calculated and N that you have given. So by putting that relevant values at the end, you will have the power is equal to 120 kilowatt. Similar example that you have given, once again, there is a hollow shaft and we transmit 200 kilowatt power at 80 rpm. And the limit for the allowable shear test that you have given is 60 megapascal, and internal diameter and external diameter relation is like that. Internal diameter is 0.6 times that of the external diameter of that shaft. Just you require to calculate this diameter internal as well as outer diameter. So for that, kindly go through torque equation. T is equal to pi by 16 into tau d raised to 4 minus small d raised to 4 upon d. By putting that value, you will have a 10.3 into 10 raised to minus 6 into d cube kilonewton into meter. Now we also know that the equation for the power, that is equal to P is equal to 2 pi nt divided by 60. So by putting the values or magnitude of power over here at the end, you will have the diameter is equal to 1.32 into 10 raised to 2, because RPM that you have already given and T that you have already calculated over here. So by putting that all of these values into equation for the brake power or simple power equation, you are getting the diameter that is equal to 132 mm. And you have also given the relation for internal and external diameter, like d small d is equal to 0.6 into capital D. By putting that value over here, you are also able to calculate internal diameter, that is 79.2 mm. So dear student, this was specially session that we have taken on chapter torsion, in which specifically we have discussed about strength of solid and hollow shaft. We have also derived a torque equation. We have discussed about the performance parameter, and at the end we have also solved a few examples based on those theories. I hope this lecture will definitely help for the improvement of your technical knowledge, especially in case of machine design and machine component design sectors. Still, you are having any query related with my this video lecture and topics and subtopics, let me inform. We have a solution. Thank you very much, dear student, for your kind of patience to attend my video lecture. Thank you very much.